Good afternoon, everyone. My name is Franca Tamaris. I'm the Events Coordinator for the Melbourne Energy Institute. Welcome to our seminar today on blue hydrogen as an alternative to natural gas. Before we begin, I'd like to acknowledge that today we're gathered on the lands of the Wurundjeri, Woiwurrung and Boonwurrung people who've been custodians of this land for thousands of years, and we acknowledge and pay our respects to their elders, past and present. Thank you for joining us for the sixth seminar in 2025, focusing on gas. We've had some interesting seminars, which we have recorded and are available on our website to view. Some instructions to our online audience. If you have any questions, please enter them into the Q&A box as a chat function is disabled. We will have more time for Q&A at the end of the session, and we'll endeavour to get through as many questions as we can. I will now hand over to Professor Michael Breer, who will moderate today's webinar. Thank you.
Thanks, Franca. Can you hear me? Terrific. And hello, everyone. Nice to almost see you all. My name's Michael Breer. I'm a Professor of Engineering at Melbourne University, and I used to be Director of MEI, but I'm no longer anymore. So good to see some of my previous colleagues and associates. Today, I'm moderating a very good colleague of mine, Professor Simon Smart from the University of Queensland. Simon is Deputy Director of the Dow Centre for Sustainable Engineering Innovation and a Professor in the School of Chemical Engineering at UQ. I know Simon best from our work together on the NetSec Australia project, and if Simon doesn't plug our big seminar next week during his talk, then I'm plugging it now. That's a project between UQ, Princeton and Melbourne on the Australian Decarbonisation Task. Simon's own research focuses on sustainable production and use of energy and chemicals, including the development of technologies and processes for the production of clean water, clean materials, and clean energy. So there you go, that's the triumvirate, the trifecta. Simon's technical research looks particularly at inorganic membranes, hybrid nanocomposite materials for gas and water separation, and the use of molten metals, salts, as catalysts for hydrogen production through things such as methane pyrolysis and CO2 utilisation and other pathways. Previously, Simon's worked on the Rapid Switch Initiative with Princeton since its inception at the Dow Centre for Sustainable Engineering Innovation. So thanks everyone for joining us today, and I'll hand over now to Simon to give our talk. By the way, if you've got any questions, put them in the chat, and at the end of the session, we'll in the Q&A, and then in the session we'll run through all of those. Thank you.
Thanks, Michael. I also appreciate the promotion to professor, but I'll take it as an associate professor at the School of Chemical Engineering. Thank you very much for having me today. It is wonderful to talk again on blue hydrogen as an alternative to natural gas. I too would also like to acknowledge the traditional lands on which we're meeting. I'm coming to you virtually from Quandamooka country in the Redlands in Queensland. So I thought I would start by talking about hydrogen as an alternative to natural gas. Hydrogen has clearly become central to discussions about net zero because it's a very versatile molecule. And this flexibility is what allows it to be a substitute for natural gas across a number of sectors that I've put up there in the slide. So we'll focus on, the majority of my talk will focus on the production of blue hydrogen, but just to give a sense of where it can be used as an alternative to natural gas. So industry heat, I think, is probably one of the main focus areas for hydrogen. It can look to replace natural gas for very high temperature processes like steel or alumina. potentially for cement, although I note that there are very few demonstration projects where hydrogen as heating for cement is used or proposed, although the Calex and their Lilac technology could use hydrogen as well as a range of other fuel sources. These are basically processes where electrification is really hard, really tough. And I think it's important to note here that actually there are just no alternatives, or that there just doesn't exist any high temperature, low carbon, low cost heat. You can have two of those three, but you can't have all three together. So hydrogen, at the moment anyway. So hydrogen can be used for industrial heat. It's also very important as an industrial feedstock. It's already used in, chemicals like ammonia or methanol. But then we can also think about it in terms of the steel industry, where we can use it as a reductant instead of coke and coal. And so that's the other really important place. Energy storage has been talked about for a while. And we can think about this in terms of either gas blending hydrogen into the gas network for immediate use with turbines, or we can think about the storage of hydrogen for use as a gas into a turbine by itself, or for fuel cells on a much smaller basis. An energy vector is one that I'll talk about a little bit in a second, as a very interesting way of moving energy around, particularly in places where it's difficult to move electrons, like across country borders or as an export from Australia. And we can see that, there are a number of our export markets that want low carbon energy vectors for things like hydrogen or hydrogen derivatives. And then mobility is the other one, where hydrogen could be used in sort of heavy vehicles or heavy haulage vehicles, usually paired with a fuel cell. The question then becomes, when does blue hydrogen become useful in all of these? And I think we'll see as we go through that it's largely about a potentially lower cost and a more productive or an easier route to scale in comparison to green hydrogen, where green hydrogen stands currently. In terms of the Australian hydrogen opportunity, and this is one of the slides where I'm going to plug Net Zero Australia, our website there. And as Michael said, we've got an update to all of this next week. These are our phase 1 results. But essentially, when we look at the potential opportunity for hydrogen as an energy vector, as an export vector in Australia, we have tremendous opportunity. So in the study, we actually modeled both the domestic and the export system, and we said, let's swap out all of our fossil energy exports for an equivalent energy amount of a hydrogen vector. And so we're on the order of sort of 140 to 150 million tons of hydrogen being exported by 2060, which is, I guess, an extreme kind of scenario, but highlights what the world requires of Australia at the moment in terms of energy. In terms of what that story looks like, in the majority of cases, our modeling showed that initially blue hydrogen features, but as the cost of solar and electrolyzers and other renewable energy and storage comes down, green hydrogen largely wins that race. These were 2022 numbers, 2023 numbers, or costs. And so there may be, recent changes to cost data may influence that. And we've seen quite a few green hydrogen projects delayed or mothballed in recent years as a result of cost projections. In terms of where it was used, predominantly to in transport, to iron and steel and other industry applications in these three colors in the middle here, and then the potential for making liquid fuels from hydrogen as well, decarbonized liquid fuels from hydrogen as well. I'd be remiss if I didn't show one of our awesome maps, which basically highlights sort of where hydrogen facilities might be made, largely for export in Australia, where these sorts of large areas in the middle represent, I guess, the scale of solar and some wind and pipelines required to export the same amount of energy in the form of hydrogen that we do as coal and natural gas today. That sort of paints an overview. I'd like to then move into what's essentially a discussion of how we make blue hydrogen. But I thought it's important to remind the audience, many of you I'm sure will know, some of you may be less familiar, but given that hydrogen is, you know, from a physical perspective, a odorless, colorless gas, but the way we like to think about it, we assign hydrogen colors. And so when the 90-something% of the world's hydrogen right now is made from fossil feedstocks, and that gets sort of anywhere from black hydrogen for coal through to gray hydrogen for natural gas. We have white hydrogen, which is around naturally recurring underground reserves, gas reserves that have high hydrogen contents. And then blue, which is essentially characterized as fossil. So we're still using a fossil source, but we're adding carbon capture and storage to it. I've got turquoise here, and I will talk about this a little as it's one of my own research areas, as Michael mentioned earlier in the intro, and that's methane pyrolysis. So this is the idea of thermally decomposing methane into hydrogen and solid carbon without making carbon dioxide. And it's turquoise because it's not quite blue and it's not quite green. We have pink hydrogen made from nuclear sources or nuclear electricity. Green hydrogen from renewable energy fed into electrolyzers or using biomass, and then photocatalytic, so essentially direct conversion into hydrogen using sunlight for gold hydrogen. But there is a little bit of an elephant in the room, which is blue better than gray? And so this all started, there was a 2021 study that started a very interesting debate. They asked the question in their title of their paper, how green is blue hydrogen? And the original and in some circles, somewhat infamous study is shown here on the left, where we can see that blue hydrogen, these two cases here, is actually, you know, quite comparable with gray hydrogen in terms of the emissions intensity per unit of heat delivered, which is clearly not what we're looking for in a decarbonized world where hydrogen is being used as a replacement for a feedstock or an energy vector. And in fact, when compared with the combustion of ordinary fossil sources, blue hydrogen in their analysis was actually worse than natural gas or coal. And you can see that the large portion of the emissions in red here is actually methane, which is essentially leakage of the natural gas supply chain. And given that methane is, you know, 86 times worse on a 20-year time frame than CO2, small leakages of methane correspond to a large emissions intensity. Now, as I said, this is a contested space, and so there've been many academic and other industry articles that have looked at this in more detail. I put an example of one of those on the right-hand side here, which essentially looks at sort of some of the, or challenges some of the assumptions that were made in the original article around the energy efficiency of these blue hydrogen processes. Sorry, I don't know what happened there. These blue hydrogen processes, and also looks at the methane leakage rates associated with the various infrastructures. I'll note the original study largely lent on what they understand from the US infrastructure, so all the supply chains within the US. And so it's not necessarily comparable to Australia. But what this study looks at is essentially showing that in using their assumptions and analysis, blue hydrogen was anywhere between 30 and 60% better, or a reduction on emissions intensity compared to grey hydrogen. But as we haven't built many blue hydrogen plants around the world, this is still a contested space. Okay, so what I would like to go through for the next few minutes, or through to the end really, is the different production ways in which we can make blue hydrogen. And I'll focus on coal and gas because they're the predominant feedstocks in a country like Australia. And the majority of this, well, all of this work is a result of, or comes from some of the work that we did with the Future Fuels CRC. And so I'd like to, if I forget to do it at the end, I'd like to acknowledge their funding support for this particular piece of research. So let's start with coal. So there are multiple ways that we can there are multiple different sort of reactor processes that we can turn coal into hydrogen, but they all use I guess an overarching process called gasification. And gasification is basically where we take a carbon feedstock like coal, and we add heat and a little bit of an oxidizer, so a little bit of something like steam or oxygen or air. We do it at high temperatures, moderate pressures, and instead of completely burning into carbon dioxide and water, we end up making a product called syngas, which is a mixture of hydrogen, carbon monoxide, and carbon dioxide. And this syngas can then be transformed through a range of different chemical processes into gaseous and liquid fuels and chemicals, or we can just focus on purely on hydrogen production. There are a range of different gasifiers that are out there. These are big process vessels, high temperature, sometimes pressurized. When I say high temperature, I'm talking sort of 800 to over 1,000 degrees, depending on the technology. And some of the major sort of equipment manufacturers around the world have all had a go at making various types of gasifiers. What we've focused on is an entrained flow and a dual fluidized bed gasifier. These are some of the more common types of those that are out there. And we ended up looking at using both Queensland black coal or a Victorian brown coal as feedstock. So in the first instance, this is a very simple process flow sheet or block flow diagram for the entrained flow gasifier, where we're using both steam and oxygen. So in the case of Queensland black coal, we need to make a slurry before we feed it into the gasifier. In the case of brown coal, it's already quite wet, so actually we have to dry it before we feed it in. And we're feeding in pure oxygen alongside steam to do the gasification. That produces our syngas. We then pass it through what's called a water gas shift reactor, which converts all the carbon monoxide into carbon dioxide, and in the process gives us more hydrogen. And then we remove the carbon dioxide, send it through a purification unit, and we get our hydrogen product. Now, in this sort of a process, there are two places where carbon dioxide is made. One is through the actual gasification process, and the other is through the addition of heat when we generate steam. And so we modeled this by removing CO2 from both sources. The other process is this dual fluidized bed process. And in this instance, we focused on Victorian brown coal, again, dried in the pre-treatment section. A steam gasifier, essentially the same process. The difference on the downstream side, the difference here is that we also looked at not only a sort of an external heating process, but we also looked at in situ capture. So this is a sort of like a chemical looping process where we're adding calcium oxide and retrieving calcium carbonate from the reactor as our way of removing the CO2. It's a different way of doing the CO2 capture. In terms of what we look at, this is just a pretty simple performance comparison. I think the things to note here are that we have a slightly lower feed rate. We require slightly less coal if we're feeding in steam and oxygen than we do for the process that only uses steam. We can have really quite low CO2 emission intensity. So this is just a modeling study, and we've assumed a fairly high capture, greater than 95%. And so we end up with quite low CO2 emission intensities, sort of less than, in some instances, less than half a ton of CO2 per ton of hydrogen, which in an unabated process would be on the order of sort of 15 to 20 tons of CO2 per ton of hydrogen. But I think what people are probably more interested in is what does that look like on a cost basis? So the capital cost between the two, which is the chart on between the four different cases here, is the chart on the left. And we have relatively similar capital costs across all the processes. The main one, or the cheapest option, although it is the least demonstrated, and so there's a lot more uncertainty associated with this in situ carbon capture case 4, is the Victorian brown coal dual fluidized bed with carbon capture. We can see that the gasification in the pinky color here represents a significant portion of the capex, as does the CO2 removal units and the dehydration and compression. So CO2 processing and the gasification and coal processing represent the vast majority of the costs. If we then transfer that to a levelized cost, so dollars per kilo of hydrogen, we are looking at somewhere on the order between $4 and $5 a ton, based on our operating assumptions. Now, I note that a couple of, I think it was last week, EPRI, the Electric Power Research Institute, released a report that they entitled, I think it was around using Australia's coal to produce hydrogen for Japan. And they had costs in their study, which used slightly more updated numbers, of around $4.50 US a kilo, which is equivalent to about $6.70 a kilo. But the differences were that they had a higher coal cost. So their coal cost was about about 115 US per ton, as opposed to our $70 odd per ton US. Their plant was 7 times larger than ours. Our basis was 100,000 tons a year, as opposed to 700,000 tons a year. And the big difference, though, was that they actually took the CO2 and instead of storing it in a nearby reservoir, shipped it to Malaysia for storage. And that added about 20 to 25% to the cost. So if we do a comparative case, then our Queensland black coal, which is our case 1 here, would be a rough about $6.60, $6.70 Australian per ton or per kilo of hydrogen. So actually really quite good agreement across several years, which indicates that the technology hasn't, the costs of the technology haven't dramatically changed in the intervening time. If we do a bit of a sensitivity analysis to see how low we can go, the coal price and the capex have the largest impact on price. And if we look for an everything minimized price, then we're looking at a levelized cost somewhere between the $2.70 and maybe the $3.30 mark, depending on the technology. In most cases, the Victorian brown coal comes out, or in all cases that I've shown here, the Victorian brown coal comes out as the most prospective case. Not quite the $2 per kilo, but certainly approaching it. I'd like to move on then. So from coal to methane, to using natural gas effectively. And again, we've got a couple of different options here. So we're doing the same thing where we are not quite completely burning or completely combusting the fossil, the methane. So we're feeding in either just enough or not quite enough oxygen to burn it properly in the case of an autothermal reactor, or we're using steam as the oxidant to crack the methane. And so the two technologies that I'm going to talk about are steam methane reforming, SMR, very different to the SMR in the nuclear small modular reactors. This is steam methane reforming. And the other one is ATR, which is autothermal reforming. So the difference here is that in a steam methane reformer, we're typically supplying heat from outside, and we are using steam to crack the methane. In the autothermal reactor, we are mixing everything together, feeding in oxygen, but not enough oxygen to burn it completely. And that's what makes our syngas, so it's direct heating. So, and again, these two technologies are amongst the most common ways that the world produces hydrogen right now. What does that look like on a process flow sheet? Quite similar to the coal process flow sheet, particularly the back half around the water gas shift, the CO2 removal, and the hydrogen purification. The upstream or before the reformer, which is what does all of the work, there's some pre-treatment as well. Excuse me, there's some pre-treatment as well. And we've got, again, two places where carbon dioxide is produced, both from the process and also from the heating. And in our study, we're capturing both of those. Autothermal reforming, we actually looked at two cases here. One where we're trying to maximize the amount of CO2 that we captured. So you'll see it called maximum capture. So again, removing it from the process as well as removing it from the combustion gases used to provide additional steam into the process, versus an option where we only look to remove the CO2 from the process emissions, and we effectively emit the small percentage of flue gas emissions from steam generation to the atmosphere. This enhances our efficiency because we have less energy lost associated with CO2 removal. And so we've called this our maximum efficiency case. If we have a look at it on a comparison basis, we can see again, so tons of natural gas per ton of hydrogen, somewhere between 3.5 and 4, depending on the technology. Our CO2 intensity, if we don't use carbon capture and storage, then our CO2 intensity is around about the 9 to 10 tons of CO2 per ton of hydrogen. So about half that from coal gasification. And then we are on a similar sort of emissions intensity, around the sort of 0.7, 0.8 through to about 1.5, where we don't capture everything across the three technologies. You'll note also that we've got a slightly higher energy efficiency because actually some of these processes can produce extra steam, which can then be turned into electricity, either used for the plant or exported back to the grid. So the efficiency can be slightly higher for all of these. Again, let's look at costs. So from an installed equipment cost, and again, this is 100,000 tonnes a year, which is relatively small actually for both of these plants, and probably favors SMR. ATR, autothermal reforming, gets more economical with scale. We see that the maximum capture has the highest capital cost, and the major components are, so although the max efficiency and the standard SMR are quite similar, the major components of the cost of the capital cost are the CO2 removal units, the reformer itself, and in the case of the autothermal reformer, we need to separate oxygen from air, and so that's a significant portion of the capex there in terms of the ASU. If we then go to the levelized cost, these are slightly lower than what they would be. These are slightly lower than what we saw for coal, sort of between $2.90 and $3.20, depending on the technology, with the ATR coming out slightly ahead. We used in these instances, so you can see here that actually natural gas has the highest contribution. So the price of the gas is super important. For context, we used $6 a gigajoule for our gas price, which, if we have a look at the current gas prices in Australia, at least on the East Coast, is about half what they are today. So if we incorporate that, it's basically like $11.70, $11.90 today. So if we make it $12, it's about it takes these up through to about $3.90 for SMR, through to about $4.30 for the ATR max capture, and $4.15 for the $4.15 for SMR, $3.97 for ATR max efficiency, and $4.32 for ATR. So it's about a 30 to 40% increase in cost associated with using today's gas prices. So clearly, the gas price has a huge impact on these technologies. Again, doing a bit of a sensitivity analysis. So if we're looking at getting down to our $2 a kilo target, then we need both low natural gas prices and substantial capex reduction. So if a 30% reduction in capex and $2.50 a gigajoule price for natural gas takes us down under the $2 for two of the technologies, which is $2.50 versus what we're seeing at the moment, $10 to $12 a gigajoule regularly, is quite ambitious for reaching that $2 target. We also, as I guess my final point here, is that we know at larger scales that, as I said, ATR will become more capital efficient and more competitive as a technology at the larger scales than what steam methane reforming is. Okay, and in the last 5 minutes, I'd like to talk through to leave us, or last 5 to 10 minutes to leave us some time for questions. I would like to talk through methane pyrolysis, which is a bit of an emerging player in the blue hydrogen space. As I said, most people sort of call it a turquoise color, not quite blue, not quite green. And what it is it's basically taking methane, the CH4 here, adding heat, but doing it without any oxygen or steam around it. And so we end up producing hydrogen and solid carbon. So it's effectively, if we can control leakage from our upstream methane supplies, it's effectively a CO2-free way of making hydrogen. As in, there's no carbon dioxide produced from the process, because the oxygen never comes in contact with the hydrocarbon. Now, we make a solid carbon. That can be a byproduct, but it can also be a problem because, so one, we make a lot of it. For every ton of methane that we make 4 tons of carbon. So if we're talking about making lots and lots of hydrogen this way, then we're going to make lots and lots of carbon, and we need to think about what that will swamp a lot of the potential solid carbon markets. But also it does bad things for our reactor if we're not careful. Traditionally, it would deactivate catalytic surfaces, plug up gas flows through reactors, and the way in which it was dealt with previously, if you wanted to make hydrogen this way, was basically you just burn the carbon, which then of course negates the whole impact of having this as a CO2-free way of making hydrogen. So let's look at a couple of ways of doing this differently. And I've got some slides coming up that look reasonably complex, but there's 2 basic technologies that I want to talk about. One of which is using a solid catalyst. So something like, or an expendable catalyst almost, or like a reactant, but not quite a reactant. So this is similar to, there's an Australian company, Hazer. This is similar to their process, where they're feeding in a solid catalyst that can accumulate carbon, but they can remove it from the reactor and extract value from it in a sort of a fluidized bed process. The one which I'm more familiar with and have done quite a bit of research on for the last 8 to 10 years now is using molten metals or molten salts, where we're effectively bubbling methane through a bath of molten salt or molten metal. The idea being that the density difference between the carbon and the molten media will now enable it to float, but also, and therefore be removed. But also, as the bubble's rising up through the bed or through the molten liquid, we are effectively continually exposing fresh catalytic surface, so we never get deactivation. But of course, the flip side is we have to deal with liquids at sort of 800 to 1,000 degrees, and ideally in a pressurized situation. So we're talking low TRL technologies here. This solid catalyst, and I'm probably mischaracterizing for the Hazer folks, they're building a demonstration scale plant, the second plant, I think, at the moment, which will demonstrate this at scale. The molten media one is at a much lower level of demonstration around the world at the moment. So what do the flow sheets actually look like? So in the case of the solid catalyst, we've effectively got our natural gas coming in, do a little bit of pre-pyrolysis to get rid of some of the higher, or the C2, C3, the ethanes, the propanes, crack them, and then send everything, the majority of methane, into the pyrolysis reactor. The gas can be taken out the top, taken off, well, we might need a cyclone or something to clean out the solids, but effectively straight into purification. The tail gas can come off to add additional heat back into the reactor, which may also necessitate some sort of carbon capture from the burning of small amounts of carbon there. And then we've also end up with our solid carbon separation at the end, where we might want to take it either for disposal or for use for sale as a byproduct. In terms of the other options around molten media, it's a similar process where we're pre-pyrolyzing, sending it into the pyrolysis slurry bubble column reactor. Hydrogen can come off the top and be purified. We do have to have a loop where we need to do carbon separation and heat molten salt, and that heating of the molten salt will typically either be through natural gas or through the hydrogen product or the tail gas product, which then also results in a small number of CO2 emissions, which can be captured and sent to storage. And then we've also got our carbon handling. Now I've got these two crosses here to indicate that actually this could also be used to produce a hydrogen methane product for blending directly into a pipeline. So we've only got hydrogen and methane here, and so under situations where we're taking 10, 20% or 5-10% of hydrogen in a pipeline, this could be effectively directly injected in, thereby negating a significant portion of capital for hydrogen purification. We can also use renewable energy here. So in these instances, we're looking to remove that production of, we're looking to replace some of the heating requirement for the pyrolysis with electrical heating or solar thermal heating, and so to replace some of the combustion of the tail gas or natural gas in order to produce the heat for the reaction. And so that's this integration on both sides is what we've looked at as additional cases here to see how the impact of using less natural gas but changing it for electricity plays out. In terms of our performance, I've got more cases here. In the interest of time, I can't go through them all. But what I will say is you can see that the emissions intensity, even for the one where we don't have CO2 capture, is quite low, sort of on the order of less than a ton per ton of CO2 per ton of hydrogen. So again, it's not quite green, but not quite blue. And we are producing anywhere between 1 and 3.5 to 3.6 tons of carbon, solid carbon per ton of hydrogen. The efficiency of the process is a little lower because the pyrolysis reaction actually requires energy. It doesn't generate it because we're not fully burning the carbon. From a cost perspective, levelized cost, we are looking on the order for most of these in the high $3s to low $4 a ton. Again, with our low natural gas price of $6 a gigajoule, if we raise that to $11.90 a gigajoule, then these prices change from about $5.25 to about $5.90, depending on the technology choice. And we can see that the natural gas feedstock is the significant portion, as well as the capex. The green bars here represent those renewable energy cases where we are swapping some natural gas use for an increase in electricity or renewable electricity with that renewable energy integration. This is a bit of a misnomer in terms of this is our blended product, so it's not pure hydrogen. So it has substantially lower capex as well as overall requirements because we're not making pure hydrogen. From a sensitivity analysis perspective, the natural gas, the capex, and actually the byproduct cost are major drivers here. So if we're looking anywhere between a $0 disposal cost all the way through to some high value product at maybe $500 a ton, it swings the overall price quite substantially. And we see that play out in the sensitivity analysis where at a very high byproduct carbon price, if we can assume that we're going to end up with something really quite special in terms of the carbon product because of how we've controlled the chemistry, which is yet to be proven, I will add, then we're looking, around that $2.30 to $2.80 a kilogram of hydrogen, which is not hitting our target, but is getting closer. Although there's a lot of uncertainty in these values because this is still low technology readiness technology. In terms of the impact of learning curves, we did a little bit of change to the learning rates for the emerging technologies. And we can see that under high learning rates and very favorable natural gas prices, then we end up in a position where the emerging technologies might be comparable to our conventional technologies as they stand today. And with that, I'd like to wrap up and be ready to take questions. I guess I'll finish by saying that blue hydrogen, I think in most people's minds, is a transitional process. And as it stands from a technology standpoint, natural gas is probably the most promising pathway, but it's highly dependent on the natural gas price. And so East Coast gas prices do not make that favorable. And so with that, I'd just like to acknowledge the folks who did all of the actual work that I get to talk about and the Future Fuel CRC funding, and hand back to Michael to moderate questions.
Brilliant, Simon, thank you. And we've had some questions online, and I've taken records of those, but I encourage the 64 participants present to fire up some more questions in the Q&A, and we can get into it. So terrific talk, Simon, thank you. I'll kick off with some of the questions that we've got. Oh, good, there's some more coming in as well, thank you. Keep them coming. As the price of natural gas has increased a lot, and it's caused the closure of fertiliser plants, etc., in Australia. How might you therefore use blue hydrogen production in urea production?
Yeah, that's a really good question, and I think it sort of answers itself in the sense that it's the high natural gas price that has shuttered the ammonia plants. It's also going to be a high natural gas price. It's also likely to be a high natural gas price that makes blue hydrogen uncompetitive. In those instances, we could look to see a coal-based pathway, particularly some of the Victorian brown coals. That I think that would be in a situation of high natural gas price. Coal is probably the only pathway that we could foresee where blue hydrogen would play a role in something like ammonia or other sorts of processes that utilize hydrogen as a feedstock.
Good. Yes. If we're shutting down plants for the high gas prices, turning it into something else before you use it doesn't help in that regard.
No.
And it's a particular. The Victorians online will know about Qenos shutting recently, and that was purely driven by gas prices as well, in that case making plastics. Or actually olefins, previous plastics. Now, next question. Do you have a view on the cost differences of local CO2 storage versus storing overseas, and how that might affect the cost of making blue hydrogen?
That's an excellent question. And I don't have a view because I don't think we have data. Obviously, compression and shipping will add to the cost. And as I said on that recent EPRI study for using Queensland coals to send hydrogen to Japan, the CO2 transport and storage cost to send it and store it in Malaysia was about 20 to 25% of the total levelized cost of hydrogen. So that's quite substantial. So, and more substantial than the CO2 transport and storage costs would be in our study. But I don't have any hard data to back that up because there's just not enough around in terms of CCS projects around the world. So intuitively, you would think storing it locally, but the regulatory environment, I'm in Queensland. Last year, we banned CCS in the Great Artesian Basin, making it a very difficult prospect for Queensland proponents. But yeah, I don't have a strong view because I don't have any data to base it on.
Yes, yeah, and my guess is that if you ask a company how much they'll charge for sequestering the CO2, the first question they'll ask you is, how much have you got?
Mm.
So if I buy one pair of shoes, I get one price. If I buy two pairs of shoes, I'll get a different price. So some other questions. That's great. Thanks. I've got plenty of questions now. Now, referring to slide 23, why does the maximum efficiency of ATR show a higher CO2 intensity compared with the maximum capture rate? So I think that properly.
Yeah, so if I can just really quickly go back to that slide, it's basically because we're not capturing. That's the ATR, wasn't it? This one. So it's fundamentally because there is some CO2 produced in steam generation that's not part of the actual process. So there's CO2 made in two parts of the plant. And in the max capture case, we capture both of those. And in the max efficiency case, we only capture the majority of the emissions, which come from the process. And the emissions associated with combusting natural gas for heat and steam provision in the process aren't captured. They're just released to the atmosphere. So that gives us a better efficiency, but it has a consequently higher CO2 intensity as well.
Thank you. Now, we've had a few questions about how much does CCS cost. So I think we've kind of answered those. That is, short answer is we don't know. And it'll be location specific.
Extremely location specific.
So here's a question. We've had closer of government corporate projects on hydrogen, probably fair to say mainly green hydrogen, with economic and technical feasibility being stated reasons. Can blue hydrogen push the needle given this current situation? Good question.
That's an excellent question. I think there are, so globally, yes. In Australia, again, it's very location specific. On the East Coast, I don't see gas prices coming down anytime soon. And maybe Michael or some of the many folks online will have a dissenting opinion. I don't know, but I don't see them coming down anytime soon, which makes blue hydrogen from natural gas uncompetitive. And making it from coal is a less I guess the technology readiness level, the development level of making it from coal is slightly less, and it's difficult to see proponents willing to take on the really enormous capex requirements to build these gasifiers. So having said that, on the West Coast, gas prices are much lower. And so it may look prospective over there. But again, we've got to find a CO2 storage reserve, and we haven't characterized enough of those. So I think it's quite uncertain in an Australian context. And then my favorite one, which is pyrolysis, is just still at the developmental stage. So it's too early really to say.
Yes, yeah. So Another question. Actually, by the way, before I get to the next question, I'd add one other thing, a little bit like the question before about the cost of CCS. Who's going to buy the hydrogen? Who wants it in significant volumes? And that's a key challenge. I actually think there are big opportunities for using hydrogen, green or blue, particularly blue, in significant volumes, but they're not obvious yet. And a lot of people talk about making it, but we're not hearing a lot of people saying, I want to buy it in large volumes. It'll justify these things. So that's the problem in markets with supply and demand.
Yeah, excellent point.
So next question. What markets do you see for the carbon produced in your processes?
So there's a couple. If it's a low value product, then there has been some work that's shown that adding it to products like cement or bitumen can actually improve the properties of concrete, for example. Concrete is probably the only market large enough that could absorb an entire hydrogen industry made from pyrolysis, but it could do it. For the other option, the other potential targets could also be for use in steel making as a replacement for coke, or as an additive with coke. You run into some issues with the CO2 accounting in that instance. And if you can make high value products, which not enough people have demonstrated yet, then you could start looking at sort of carbon black or sort of battery anode markets, battery electrode markets. But I don't think we've seen that at a sufficient technology demonstration at this stage to say that we could confidently access those markets. I think it's going to be a low value, high volume application.
Yeah. And I might ask one more question and then we'll wrap up. And this is a more political question. So the Victorian Minister, Lily D'Ambrosio, has not supported hydrogen from coal. Why is that the case? And what might people do for components of hydrogen from coal to maybe change that position by the Victorian State Government?
They are excellent questions that as a Queenslander, I can't add a lot to, but Michael, perhaps you have a view.
This isn't a Dorothy Dixon. This is from one of our attendees. Well, I'm a bit like Simon, like before, you have to ask the CCS proponents if they so charge CCS. You have to ask the Victorian Minister those questions. But the HESC project is having some challenges. But I'm not close to the HESC project. I think my understanding of it is that its costs of hydrogen production are as low as that people hoped. But there was a little bit earlier discussion, Simon, it was who wants the hydrogen in significant volume for a given price? And
Yeah.
maybe if people put their hands on it and said, we'll buy this amount for this much, and that's financeable to build something of significant size to do it, then that would be a different discussion.
Yeah. Yeah, I think that the draw from the demand side or from the user side is lacking. I think we see that for green hydrogen as well, although they're also challenged on cost prices. But without end user demand, it's really difficult for these technologies to come down the cost curve because we just aren't deploying and learning as we're doing.
Yes. So let's see how we go. But challenges, I think, ahead for this place thing. By the way, it's not the only energy technology that's facing some headwinds. So a bit of that across the board. All right, that's 3 o'clock. I think we'll wrap it up there. Thank you, Simon, for giving a wonderful talk. And if you thought Simon was fantastic today, he'll be just as good next Wednesday night, but he'll be in person at Melbourne University presenting the Net Zero Australia project. So Google that, and please come along next Wednesday evening if you have a moment, or you can come online. So good afternoon, everybody. Have a great afternoon. Bye-bye.
Thanks, Michael. Thanks, everyone.
Simon, thanks, Frank.